going on, guys? Today we're going to solve a problem that involves differential equations and Newton's second law, which is pretty important in this context of problems. So first, what we're going to do is we are going to look at the problem prompt here. So a sphere of mass m is skiing down a frictionless hill. So there we go, no friction, and it makes an angle theta with the horizontal as shown at the figure. So we start from t equals 0 times t equals 0, and it's subject to a velocity-dependent drag force. So this is kind of like very important here. The air resistance, of course, and it's represented by negative BV, where V is the velocity and B is some constant. So what we're going to do, let's go and look at question 8 here. So on the dot below, we can draw a free body diagram. Let's not use the dot below because the at is very small. So up here, let's draw our own free body diagram. First, we're going to define our coordinate point here. So in this direction parallel to the slope here, we have positive x. And then, of course, perpendicular to the slope here, we have positive y. So there we go. These are our two directions. It is defined. Now, what we're going to do is we'll draw our free body diagram. So up here, gigantic dot, mg, always down to the very bottom. So f of g equals mg here. Actually, let's just draw mg for the sake of our convenience here. And then perpendicular to the slope, we have the normal force, and we have a drag force that's parallel but opposite in direction to our skier. So there's our free body diagram. Kind of, if you look at the slope, obviously there's an angle theta there. All right, let's take a look at the differential equation that can be used to solve for the velocity. So this is part B now. Part B. So differential equation. Everything starts off with Newton's second law. We got to analyze the forces in the directions. So second law, sum of net forces equals mass times acceleration, and that of course is our x direction, since our y direction looks like the skier is accelerating in the y direction, not in terms of our drag force analysis. Of course, they are going downwards in the slope, but that is not of our concern. How do we get the x direction parallel to the slope? Well, let's take a look at our free body diagram again. So for this free body diagram, we can see that we have a angle like so, theta right here, and then we have our exaggerated slope here. So we have mg going straight down, and then we have the normal force going perpendicular to the slope here. And of course, that's different from the mg going straight down. So we need this component which goes from here, makes a right angle here, and then of course it all comes down to this mg. So this, if you look at the complementary angles, the normal force actually equals mg cosine theta. So that is kind of like where we got that from, because if you look again complementary angles, you'll see that is the case. Since that is the case for the again the vertical direction perpendicular to the slope, that would mean that the complementary angle to that, the complementary trig function is mg sine theta, of course, and this is for the horizontal direction. So that's kind of like this direction right there. All right, so now we have the mg sine theta as our x direction, so we can continue with our Newton's laws. So mg sine theta is our skier's direction in terms of the gravity, minus BV is our drag force. So actually, let's just do minus F, and that of course simplifies to mg sine theta minus BV. And of course, BV is defined to us by the problem, so we'll just go along with that. But since we are again velocity dependent drag force, we cannot assume constant acceleration. Therefore, we need to do m dv dt, because dv dt is the rate of change with respect velocity with respect to time. There we go. And that is of course acceleration, but a more fine-tuned way of saying acceleration, and that also just equals mg sine theta minus bv. Now down here we have divide both sides, we get dv dt equals mg sine theta, but since the m's cancel out, it's just g sine theta minus bv over m. And there we go. That is our differential equation. So part B complete. Now let's take a look at part C. Part C says we need to determine an expression for the terminal velocity of the skier. So the terminal velocity, if people aren't familiar, is when we have a free-falling object with mg and a drag force of F, and they are of course equal to each other. So F equals mg in this case. Therefore, the object is not accelerating. The net acceleration is 0. Velocity will never change forever. So that is the final or terminal velocity, and we are going to find that. So to know, since we again know this case to be true, all we have to know is that in a terminal velocity setting, we know that a equals 0. And this implies that ma equals 0 because 0 times anything is 0, which also just implies that f, or should I say f net, there f net equals ma, which again equals 0. So Newton's second law is finished for part C. Now we know it equals 0, but what does ma equal? Well, ma equals mg sine theta. Oh, gotta get that pen up there. Mg sine theta minus bv, our drag force. So we defined this earlier with our Newton's second law for part B, and this of course equals 0. Now, what we're going to do is, since we know the velocity will never change, we can change this velocity to be v of t because we know this is a special case of terminal velocity. Now, we need to move bvt to the right-hand side of the equation, and we know that, of course, the skier's gravitational acceleration does in fact equal to its drag force here. And of course, finally, divide b by both sides, and we have the answer for part C. So v of t equals mg sine theta over b. And boom, we are within bounds. Let's check. Back up here, you can see that it says solve your problems in terms of algebraic answers, MB, theta, and fundamental constants. So far, we are just doing that. All right, final step is, of course, to determine a differential equation and solve it to get the velocity of the skier as a function of time. And we must show our steps underlined right here. All right. This is arguably the most hard part of this problem, but don't worry, if you have some integration knowledge, it will be fine for you. All right. First, let's take a look at our differential equation, but we're not going to go to the most simplified form because that is not really the best form to separate our variables. So we're going to go back to ma equals m dv dt equals mg sine theta minus bv. Now notice here that we have mg sine theta and negative bv. We can see that we can divide m by both sides again, so we can get dv dt equals just, we're going to keep mg sine theta for now. You'll see why in a second. But we are just going to divide m. So mg sine theta over m, and then there we go. That's kind of like our unsimplified form of differential equation, but it's very easy to simplify. Since we see that the m is in the denominator here, we can multiply dt by both sides. So we get dv equal to mg sine theta minus bv over m dt. But since we can't integrate v with respect to t, we need to move this bv expression to the left-hand side by dividing, and we get this lovely equation here, which is dv over mg sine theta. Again, all we did is just move this over, so we move this expression over down here, so we can have our separation of variables, and this basically equals, on the right hand side, we still have that dt over m. Now we are ready to integrate. So first of all, we can add our integrals, our indefinite integrals right here. So let's do the right hand side first because it's easier, of course. So dv, should I say dt over m is basically 1 over m, and then the integral of dt, which of course is t over m. But since we don't have a definite integral, we have to add constant c. There we go. right hand side, we need some u substitution. Now we'll just let u equal to this denominator. This is the best way to go, because you'll notice that much of this is fluff, not really stuff we need. Because when we do du, we can see that mg sine theta is constant because there's no v in there, and of course the only thing that's changing v is negative b, so equals negative b dv. There we go. That's du. And let's use blue here to denote that we are in the u world. So we have this new integral here that basically states that we have negative 1 over b as our du, and then we have our du, because we're dividing du over by dv. And there we go. This is our expression. Now, what we're going to do is we are going to move negative 1 over b to the outside here. So this just equals to, or should I say, negative 1 over b and du over u. Now is a good time to know that we can move this negative 1 over b constant to our right hand side where it is waiting for us. And so since we are moving it over, we get negative bt over m plus c, and our right hand side is, of course, actually let's remove this. This is gone, and then our right hand side is equal to ln of u, and this basically equals to negative bt over m. Since the domain of ln is all positive numbers, we can do ln of c because we know that time cannot be negative, not in the traditional sense here. So basically, this is our equation right here. Now, what we're going to do is we can solve for u. We know u, of course, is going to be the e to the power of everything. So e to the bt over m plus ln of c, which is just c. And then we know that e to the c, or c itself, can be a constant. And when you multiply exponents, that's the equivalent of bringing the power to the front. So this just equals to ce negative bt over m. This is, again, assuming e to the c is also a constant, which we can ignore. So now what we're going to do is, we know that u equals this, but what is u again? Well, u, of course, is mg sine theta minus bv, because that's what we defined. And since this equals negative ce to the bt over m, this is getting a mouthful. But there we go. We need to find c. Now, we know from our problem here, always refer back to your problem when you're doing this type of stuff. From our problem, we know that we are in rest, starts from rest here. So this is very important at time t equals 0. So what does that mean? Well, in terms of starting from rest, that just means that when v equals 0, t equals to 0. So using those initial conditions, we can essentially say that v of 0 equals 0. Plugging that in, we can see that t equals to 0, this e term cancels out, and this negative bv term cancels out. So we literally get c equals to mg sine theta, because, again, e to the 0 is 1, and of course negative b times 0 is 0. So the left hand side and the right hand side agree. There we go. Pretty simple. And we are finally almost done. Since we know that c equals mg sine theta, let's write our differential, or I guess solved differential equation once again. Minus bv equals to, instead of ce to the negative bt over m, we do mg sine theta e to the negative bv bt over m. So there we go, negative bt over m. And then we're just going to do negative bv equals to, move this to the right hand side, subtract it, and then we get mg sine theta, distribute that sucker out, and we get negative e to the negative bt over m, as always, minus 1. All right, now we have this negative b here. So this negative b, essentially, when we divide it, we reverse the order of the subtractions, and then we get v of t, because that's a function of t, equals mg sine theta, which is all constant, and b, a constant, and we get 1 since the negative sign is divided over, minus bt over m. So notice in this whole equation right here, there's only one dependent, or should I say independent variable, t, and that's just in this little e term. M is constant, E is constant, sine theta is constant, G is constant, B is constant. Everything is constant except for the t. And finally, just an observation. So we have this velocity function, so that we have the limit as t approaches infinity. What do you think that equals in terms of this function? Well, of course, we solved it. That's our terminal velocity. And hopefully that wraps things up. Everything should make sense up to this point because we have this e. As it approaches infinity, we know that the velocity will never change because the acceleration will always remain 0. So there we go, guys. That is how you solve a dynamics problem that requires a differential equation. Hopefully you learned something and enjoyed this video.